My name is Lane Mosier. I'm a forester with the Sustainable Forest Education Cooperative, and welcome to you all to our 2025 webinar series. I'm joined today by John Plissis with the Natural Resources Research Institute, a really cool drone captured background, I think. So just a couple quick announcements here, and then I'll throw to John here. But our next webinar is on Thursday, so not Tuesday, June 12th. So just a heads up there, same time. We also will be sending out our monthly update to folks. That should be coming out midweek this week. And so take a look at that email and get an idea for what's coming up, like our May 20th field day and some fire dependent forests and other field days and the like. So I'll paste some of those links, but otherwise I'll stop talking and just throw to John here. John, if you want to share your screen and get rolling. Thank you all for joining us this morning.
Morning. Thank you, Lane. I'm going to ask quick. Can everyone see the presentation? Nice. Well, again, good morning and thank you all. As Lane said, I'm John Plissis. I'm the Silviculture Research Program Leader at the Natural Resources Research Institute, and it is my pleasure to talk with you this morning about a project that we've been working on for about 4 years, a little over 4 years, the Forest Change Assessment and Simulation tool. So we'll jump right in. One of the things Lane and I talked about, if you have burning questions, certainly technical questions, pop it in the chat. I've given Lane the discretion to jump in and let me know if it's something that we need to address right away or if it can be held till the end. Sometimes with some of the more technical portions, I realize folks may have a question that's really specific, and sometimes I think it's just better to grab it instead of try to go back over it. So with that, we'll jump right in. So really, a couple things. What we're going to talk about today is really why build something like this, how we built it, introduction to and kind of a wander through the tool itself, and then kind of a wrap up of some things that I have learned as I look at the data and then digging deeper into kind of the causes and why. So with that, all good research starts with a question. And the question my boss asked me was, what are Minnesota's forests going to look like in the year 2100? We know markets are changing. We know the climate's changing. We know that people's values are changing. And, you can kind of see from the graphics I have in there just kind of how harvest volumes have declined over the past 20 years or so. And then, some of you have seen these before. This is from Kenny Blumenfeld with the State Climatologist's Office. Not just how temperatures are changing, or that temperatures are changing, but kind of how they're changing and where they're changing. So trying to look at and come up with an idea of, well, what does this mean for our forests? And so our goal within all this was, and you can read it, it's also on the website, but to deliver this spatially explicit landscape level decision tool that integrates forest productivity, ecosystem services, economic information, but help managers identify what these benefits and trade-offs are of different land management decisions and kind of these impacts that climate change will have, as well as certain things like fire, winds, damage, some of these other things that are also affecting how our forests regenerate. So what it can do, it can provide you with an opportunity to evaluate kind of what changing climate, changing markets might mean to your area of the state. What it won't do is this is not a parcel management tool of, if you've got parcel level data and you want to see growth and yield through time, forest visualization software is going to do it. But this is essentially using FIA data. We'll go into that a little bit deeper in a bit. And it is an extrapolation across the state. It's not going to help you, really understand how a parcel is going to change through time because that's just not the data that was available or useful. So, and our workflow. So one of the big things we did that I won't talk about a lot today was early on, we developed an advisory committee of about 30 different people from all across all different disciplines, economic, ecologic, social, modelers, climate, to provide advice and input into this. We characterized the current conditions of the forests We simulated that forest composition and growth through time. We created an ecosystem service valuation methodology, which we'll go in and talk about, and then finally develop and evaluate and deliver this tool, which we'll see at the end. So the main piece, the forest modeling forest change through time. So we use Landis to model this. This was what we considered the best tool available to us. Landis is some of the things I like about Landis is it's getting a little bit old now. It's over 30 years old. And during that time, people have kept adding to it. It's this really unique thing that as people develop needs, modeling needs, different things that they're trying to model or see, if it doesn't exist, they develop it. And so there's a committee then that evaluates those pieces that they develop. And if it passes muster, then they bring it into the tool. So this has grown very organically through time to the point where now it's actually a foundation. There is a board and there's technical advisors that update and bring in. And so Landis it's called Landis 2, is currently on its second iteration. And it's just this really neat thing, at least in my mind, for evaluating landscape change through time. And you kind of see as a graphic from their website showing really kind of all the inputs that can go into this when modeling. So succession itself, the way tool we used internally is biomass. So as a forest cover type reaches a certain level of biomass and then starts to decline, so peaks and declines, as canopy gaps open, then the trees that are either present in the understory or the trees providing seed as those gaps create, then that understory comes in. And as the stand further breaks up through time, then the understory grows into the overstory. And so again, it's this kind of very organic piece of a tree doesn't have to be there. If it's a seedling in the understory, it might live or it might die. If it's a mature tree dropping seed, that seed might become the next canopy, or the seed might not germinate. So there's a lot that goes on in the background of determining how that forest succession moves through time. And of course, climate and soils are major impact on that. We'll see some of that towards the end. So the initial communities, I talked about this a second ago. This graphic is almost useless. So this is tree map, and it's a 30-meter resolution pixels. If we were to look really closely, there's a lot of white space. But you know, at a range like this, it looks like the state is pretty much forested. But Landis, again, models dynamic cohorts. We use tree map, which is an FIA product. It's an extrapolation of FIA plots across the state to kind of create this forest landscape cover. With what we did, so again, we modeled all 34 of the species that are represented in FIA. So we were using the US Forest Service determinations rather than the Minnesota DNR determinations of what a forest cover type might be. So those things are slightly different. For those of you who work with the FIA data or you validate, or you've seen that, you can call for either. We use the US Forest Service species, and there's 34 represented within FIA across the entirety of the state. And so, yeah, so with each one of these cohorts, they have, of course, their own species, their own mix, their own initial age, their biomass. All that created our base layer. However, one of the key things in this, I should go back, is, my apologies, that tree map itself is 30-meter resolution. So pixels are 30 meters by 30 meters. For modeling purposes, because it takes a lot of time to run one of these models. They're very complex. We back that out to 240 meters. So each pixel. So essentially there's about 64 of these 30-meter pixels within each one of the initial community pixels that we created. And it used a majority to determine what that final pixel would be. So it wasn't just a mix of all things just jumbled in and said, well, it's this. whatever the majority within that 240 meters then was assigned to that pixel. And so that's one of those things I'll call out right away. I want to make sure everyone understands these assumptions that occurred of it's, again, may not necessarily be truly representative of that area. It's truly representative of the majority of the forest cover type within that pixel, but not necessarily truly representative of what's there. And so there may be some overestimation of forest cover types and some underestimation because of that. And that was unfortunately just one of the pieces that we had to deal with in trying to make this scalable so that we could model it. So again, Landis simulates forest growth and succession and disturbance on that spatial grid. So in this case, about 14.23 acres. It groups these species together by age and different forest cover types, grows them through time. There's a lot of background material that goes into this in terms of things about the species, wind throw, fire dependence, insect and disease dependence, life cycle, when does it enter, breakup and reinitiation, how old will the longest tree live, how old will the longest tree living still produce seed to contribute to what that next forest stand looks like. So, and within this, we were able to model harvests, fire, wind throw. We were not able to include insect and disease. So for instance, emerald ash borer is not in here. If impacts or effects from emerald ash borer, impacts and effects from spruce budworm, these are still being evaluated. Unfortunately, we thought they would be included in Landis in time for us to use them. They're still being evaluated by Foundation. In the future, we hope to have them available, but they were not available to us at this time when we created this model. So, a couple other key things within this. We talk about modeling the forested extent of the state of Minnesota. One of the issues that required us as part of the ability to evaluate water quantity and water quality impacts of forestry was that the model that we used, and we'll talk a little bit more about that in a bit, required that the forested landscape or landscape be at least 30% forest cover. And so as you kind of look at the Huck 8s here that are in the image, these were the ones that at least 50% of the Huck 12 or minor watersheds were at least 50% forested. So overall, at least 30% cover within that watershed, major watershed, and at least half of the minor watersheds had to be at least 50% forested. So they had to meet kind of those two conditions for that Huck 8 to be included. And again, it maybe doesn't give us a picture of the entire forest cover of the state, but for us to be able to include water modeling along with all the other modeling that we were doing, that needed to be the minimum. And so we just had to make the decision that since that's our minimum, that's what we're going to roll with for the forested extent of the state. The other piece of this is, as I'm sure most of you on the call realize, different ownerships have different management goals and objectives. So we went into all the data sets we could find. So including the state, federal, county databases, the BIA, USDI BIA boundaries for ownership, and then private lands. So that was one piece to determine ownership. Then forest cover. So again, using those public domain data or public agency data sets, using national land cover, the National Agriculture Statistics Services. I'm not sure if anyone has ever worked with those before. Really excellent data set, but every parcel that is within or enrolled in one of the Farm Bill programs is within that data set. So we're able to remove anything that had been identified in any way agricultural. The National Land Cover data set gave us the ability to remove certain things like all the urban areas. So there were the lands that we knew specifically were forest cover. There were the lands we knew specifically were agriculture, which we were able to remove from the data set. There were those lands that were specifically urban that we were able to remove. And there was some manual data cleaning. At the end of the day, there's about 1.3 million, 1.4 million pixels within that data set that we ultimately identified as forest cover. So lots in there. But we were able to, again, clean this up as much as possible to define what that actual forest extent is, what is that ownership, and then what are those forest cover types through that extrapolation of the FIA data. So the future scenarios. We modeled 12 different scenarios through this. There were 4 management scenarios and 3 climate scenarios. So our management scenarios were kind of the static, business as usual. What is that current harvest volume, and the assumption that forest products industry will be the same in 2100 as it is today. So whatever that harvest volume level is, that's going to be the harvest volume level in the future. Increase of 30% compared to our current harvest levels, a decrease of 30% in the current harvest levels, and then a max carbon sequestration. And I really want to be clear about this. This was the assumption that if carbon markets become a real thing that people want to manage for, we gamed out all the different forest cover types, all 34 of them, and just said, what do we do to maximize carbon? So this includes non-commercial treatments, commercial treatments, intermediate treatments, anything that we could do to maximize growth, running it through a growth and yield simulator. We looked at harvested volumes not collected, harvest volumes, and dead woody biomass, so trees that would just die, and kind of compared them. And so our comparison was, if we do nothing different than the silviculture we're already doing, or if we do all these other treatments, which yields us that absolute highest level of biomass across the rotation. So just want to be clear on that. The silviculture itself was all about carbon, not in terms of some sort of climate adapted mix of species. So, and then within the climate scenarios, and we'll talk a little bit about these in a second, was just kind of our historic climate. So essentially, what is the climate been like from 1971 to about the year 2000, compared to growing that through time out to 2100. Then we looked at a hotter and drier, or hot and dry scenario. I hate to call it drier. It's essentially a small increase in precipitation, but a much warmer climate. And then a warmer and wetter. So best thing to do is actually just show that. So I'll just jump right into that. So first, the harvest volume calculations. So we went back looking at the FIA data, also the Minnesota DNR data, as well as the Department of Interior data for tribal harvests, to try to come up with what is that estimated volume of biomass that's harvested every year, looking at kind of what those upper levels and lower levels, that confidence interval, 95% confidence interval. And you can kind of see kind of that piece through time, these lower limits and upper limits. So basically we said, about 3.35 trillion, grams of biomass is that lower level that's occurring in any given year right now. And our upper limit's about 4 trillion, 4.3. So when we looked at that decliner growth, what we wanted to make sure is our decliner growth is outside that natural range of variability on an annual basis. So when we talk about future potential, what we were targeting was a decline in harvesting from maybe that mean of about 3.8 down to 2.6, and an increase of from 3.8 to about 5.2 or so. So it's kind of important to understand of what we did was we looked outside that range of natural variability. We didn't just pick a number and say, hey, we're coming from this. We wanted to make sure that our change was significant enough that it would actually have an impact on the landscape. And for the climate scenarios, this was a lot of discussion, both within the group as well as with the folks from U.S. Forest Service, NIACS, the Minnesota Climate Action Partnership, and the State Climatologist Office. Originally, we thought we would pick something, one model from the relative concentration of particles, carbon dioxide, the RCP 8.5, and one from RCP 4.5 within this. Talking with these folks, especially the State Climatologist Office, they really made it clear. The term used a lot to us was doomsday. The RCP 8.5 is really kind of doomsday. And the best explanation I heard is if you look at the Duluth National Weather Service, so top of the hill, not down by the lake, in the last 100 years, there have been 4 days recorded over 100 degrees. Under the RCP 8.5 models, that would grow to 10 days per year. So a 250 or an increase of 250%. They said, really, it probably just won't happen, or if it does, then these are things that are the least of our problems. So what we tried to do was, and depending how well you can see this, is look at kind of this intersection between these. In orange is the RCP 4.5 and blue is the RCP 8.5. What are those models that kind of provide us that intersection rather than, again, looking at kind of very little change? Where are these things similar? And so the hotter one is this MIROC 5 model. So average change is a little over 8 degrees between from 71 to 2000 to 70 to 99. But in terms of rainfall, less than an inch, close to an inch. And the other one is this CNRM, CM5 model, which gives us about a 5-degree rise in temperature and a little over 4 inches of rainfall. So these are the kind of the two models we're working with. So like I say, I kind of hate to call it hotter and drier. There really were not any models. There was one RCP 8.5 model that's actually drier. It's the only one. The other piece in this, we often get the question, why don't we use a gill? Why don't we just mix them together? And it kind of goes back to our water quality and water quantity pieces. The water quality, water quantity needs that flashy rainfall. If we mix a gill, the individual daily rainfalls kind of fall out. Everything just becomes vanilla. And so we're not really able to, or at least from the water modeling standpoint, they were not able to look at kind of these high sedimentation, high nitrogen, high phosphorus releases that you might get with a 2-inch rainfall. So again, if everything becomes 0.1 inch rainfall every day, as opposed to drop between wet and dry periods, we just didn't get that measures that would work for those models. So we had to pick a individual model. And so again, working with folks, the Minnesota Climate Action Partnership or Adaptation Partnership, we were able to kind of select these models. They ran the GCM, the general climate models for us, got those outputs, and we were able to implement them within the model. So how does harvesting work within Landis 2? So harvesting is really kind of this likelihood piece. It's based on the ownership. How likely is an ownership to harvest? So again, the state and county, more likely to harvest, for instance, than the federal agencies. The landowners, private industrial harvests a little bit more than private individuals, but their harvest levels, depending on species, can rank pretty high. So likelihood is going to be based on what is that likelihood of that ownership. The forest cover type, how much do they contribute to that volume that's harvested? Tree species age. Those are often set within the silviculture prescription, but is it within the boundaries? Is it within the bounds of what we might consider a harvestable age or rotation age? And then time since harvest, last harvest, so that we're not kind of running back into that same stand of, if it was harvested at age 60 and our minimum boundary was 40, that one's not getting hit at age 40. We can set that. So for instance, like with aspen, if our harvest age was, rotation age was 50 on state lands, then we could say, yeah, we're not going back in until at least it reaches 40 years of age. So, and you can kind of see within this, again, kind of cutting system, ranking method, minimum stand age. So these are all things that are assigned by us within the model, and then the model itself then will kind of go in, rank the stand, find which stand ranks highest, and then select that for harvesting. The other piece within this is kind of how it defines stands and management areas. So again, we have that initial community piece. Landis will kind of group similar things together. So you kind of see this is what these red lines are, kind of this grouping of similar things. and then convert those similar things into these management areas. So once something's kind of been identified as, hey, you're similar and you can be managed as a grouping or a stand. So again, we weren't harvesting a 240-meter pixel. We were harvesting kind of those pixels that were similar. So again, a small pixel wasn't getting managed, larger kind of landscape. In most cases, that's how the universe works, but not every case. And so it often made things kind of interesting with, especially with private land holders. And then the silviculture itself. So working with the U.S. Forest Service Institute for Applied Ecology, we came up with a questionnaire that was sent out to county, private consultants, state and federal managers. There was about 14 questions. You're not seeing everything on this slide. I think that's about 8. But you can kind of see the species that we asked about. So these were the commercial species that regularly show up as harvested within the FIA data. So again, things like major associates, pre-commercial thinnings, commercial thinnings. So all across the board. So like I said, it's about 14 questions within this. So I developed that in concert with the U.S. Forest Service. They actually sent the survey out and collated the data and published that report. So we tried to get that best sense from everybody, just kind of across the board of, if you're planting, if you're underplanting, what is that? Do we do that then? Do we include that in the model when something's harvested? Then are we underplanting? What is your rotation age? Is there a pre-commercial? Is there a commercial thinning? So all these pieces. And then, of course, yeah, the regeneration system within that. So, and then is something going to be left on site? So are there trees in the overstory? So is it 100% removal or is it 95% removal of the overstory? What does that look like and what does that mean? So our wildlife modeling. So we used habitat suitability modeling. Most of you are familiar, or if you're familiar at least with wildlife habitat modeling, we use the WINGS model. John Zobel and Alan Eck, we did meet with them and talk about updates to this model. Hopefully one of these days we'll actually, when everybody has time, some of you may be aware, John Zobel was very busy with the MFRC carbon dashboard for the state of Minnesota. So we hope to come back to this one of these days. But we use the habitats or the WINGS model to evaluate habitat suitability. About 60 mammal species, 140 bird species. It is a very coarse measure. One of the things as we look at habitat modeling, though, again, that 240-meter pixel is just really small. It's too small, really, to say for any avian or mammal species, is this good habitat as this changes through time? So the minimum area for habitat or for the WINGS model to work or for the habitat suitability index was actually 9 square miles, a 3 by 3 mile or a quarter township. Felt that that was kind of the minimum area where we would want to evaluate how habitat is changing through time. And our water quantity modeling talked a little bit about this. They use the hydrologic HSPF, hydrologic surface precipitation flow model, or excuse me, hydrologic surface precipitation Fortran. Sorry, the F is Fortran, not flow. Model to evaluate water quantity and water quality. And you can kind of see all these different pieces that go into that model to give us those outputs. So again, we've got the climate data, the forest cover type goes into the model. The climate data, of course, is both that climate change through time, but it's also really that weather piece of what's happening on any given day in terms of precipitation. And then that model output comes from, or then we get those model outputs then that you can see in the tool. And so again, water quantity outputs, mean annual flow, concentration, sediment concentration, phosphorus, nitrogen. So these changes are really those mean annual flow changes from 2020, which was kind of our baseline year, through 2100. And last but not least was the ecosystem service modeling. And so again, we want to take a look at how people value these services and how that might change with any one of these models. And so Saleh Mamoun was our natural resource economist on this, and he developed a choice experiment design. Some of you are maybe familiar with these. It's essentially that willingness to pay. What would you be willing to pay to maintain something? Or what would you be willing to pay? Kind of the classic one is, not to have a nuclear power plant in your backyard. How much would we be willing to pay in your property taxes to ensure that doesn't happen? So it's that kind of question of asking folks, what do you want? So, for instance, timber production, no change, an increase or decrease, carbon sequestration. So these were all the ecosystem services that were evaluated. And then once those were evaluated, they were kind of put into these plans or groupings. So, and then kind of that additional monthly bill, what would you be willing to pay to get this kind of thing? And so I don't know that we'll take a look at that today. We can within that if we have time, but it's that concept of willingness to pay. What are you willing to pay to achieve these things on the landscape? So with that, the main event, and I'm going to bounce out of the presentation now into a web browser, and we will take a look at the tool itself and talk about that. So let me open that. And so the web address, oh, I don't think I'm sharing that, sorry. So the web address is mnforcast.org, so minforecast.org. And so if you enter that into your browser, and feel free to, you can play along. It'll take you to this. So this is our homepage. And so as you come into this, you've got this kind of this introduction. Again, you can click here to jump right into the tool. You can click here to jump right into the tool. But you can look into this About section. So this gives you the project overview. So some of the things we've talked about here today. The people who worked on it, and recognition of our funders. So the Legislative Citizen Commission on Natural Resources was the funding mechanism for this. And we will thank them now and later again for their help. For those more interested more deeply in the methodology, you can go into the methods section. So the landscape modeling that we just talked about, the habitat modeling, water modeling, and then that ecosystem services modeling and how that worked. There is a help section that has, again, kind of links back to some of these, but also these frequently asked questions. So again, kind of this concept of why an area of interest, a minimum size, why that might be, or what is the habitat suitability index, or how is carbon calculated within this? And then finally, you can just go over to the ForCAST tool itself. So once you're here, so again, right, remember the forested extent of the state, you can create an area of interest simply by clicking famous last words. All right, maybe we'll see that later. So you can create a defined area of interest based on just boundaries or just an area you might be interested in. You can select a whole county. You can select an ecological subsection. So Agassiz Lowlands, Chippewa Plains, Pine Moraines Outwash Plains. You can select by watershed. So Rainy River headwaters. And yeah, it's just not letting me create an area of interest today. That's okay. Or you can create an area of interest. Once you've selected a layer, so we'll say counties and we'll do lake, you save it. And then you can go into the scenario builder. And so you can select 1 to 2 scenarios, see how they compare through time. You can take a look at how the different management scenarios might change under the climate scenarios. So comparing how, for instance, no change in timber harvest will affect the landscape across all 3 of the climate scenarios, essentially allowing you to compare the climate scenarios. You can compare them forest management scenarios within one of the climate scenarios. or you can just look at a range of outputs. So you would select one harvesting. So for instance, no change, climate, hotter, and then look at different management scenarios. So we'll go ahead and just kind of build a simple one. So climate scenario will go warmer and wetter. So again, about a 4-degree increase, about 4-degree change in or increase in precipitation. And we'll look at no change in forest management. And so we can look at, I like cover type. I'm a forester. You save your scenario. Once your scenario is saved, then you can generate results. And we are not going to watch this grind. Depending on how big your scenario is, the area, and how much you're trying to do, this can take up to 15 minutes. It's a lot of data. So I've pulled a bunch of presets. And so this one, I decided to look at the southeast part of the state. So I just selected an area of interest, and this is just a very simple analysis. So I asked it to look at forest cover type. I picked one climate scenario, warmer and wetter, and looking at forest management scenario of maximum carbon sequestration. So your summary, once it runs, this will be the first tab that shows up. And of course, there's 6 tabs across here. We'll look at each one. So again, it gives you a recap of what your summary selection was. And because I selected forest cover type, I can just go down here and make a pick, and it will give me a bit of output for that. So for instance, aspen down in the southwest part of the southeast part of the state, not a lot. So it's 0.04%. It might increase by 0.02%. And my apologies, I originally had the white oak, red oak, hickory group in here. So again, it's about the largest group in here. It's about 7%. It's going to increase by 1.18% or increase up to about 8.2%. You can go to the trend charts. And one of the things that's really neat about this, or not, but you can click these on and off. About 80% of this area is non-forest, which is predicted to grow by about 2%. So we're going to have some forest loss here. But once you get rid of that, some of the other things show up quite a bit better. Again, the major species here was white oak, red oak, hickory, or the cover type was white oak, red hickory, and the mixed upland hardwoods were the major species. As you can see, the white oak, red oak, hickory group is forecasted to grow from about 6.58 to about 7.76. So between 2130, actually, 2120 is kind of not on here because it's our base year, out to 2100, we'll see some increases here. With these, the same thing goes. I can click things on and off. It's not maybe as obvious in this one. We'll take a look at another one in a second where it's a little bit more obvious. Distribution. So this one is because it's a little simple. Again, you can download these charts, sorry. The radar charts of just maybe how things might change through time. You can get into maps. So these are, you can get hex bins. My apologies, these can take a little bit of time to build in sometimes. A hex bin, a contour, or a heat map. You can compare the different scenarios available to you. In this case, really, we just didn't have multiple scenarios. Again, there's the heat map version, the contour version, the hex bin version. And you can animate to see how that changes from 2030 through time. So you can see the dates changing here. And again, I can click species on or off within that, so I can see how individual species might change through time. And then the economic valuation piece we talked a bit about before. And because we've got the simple scenario, it's not running that. Last but not least, you can share this. You can download a full paper report, your area of interest, kind of what those outputs are, the trend charts through time. And again, you can kind of click some of these on and off if you want to limit that. You can download this report, or you can copy it and send that link if you want to share that with someone. So let's go into something a little bit more complex. So with this one, I selected that ecological subsection. So this is kind of going back to that one's still building, sorry. This ecological subsection, and looking at kind of the climate. So this is a comparison of how all three of the climate models, looking at just one harvest. So forest management, no change in harvesting, comparing all three of the climate models. And I'm looking at how forest cover types will change. So within the summary scenario, the website designers basically just said, hey, the top three changes. So it's not necessarily anything you might pick integrally. It's just those ones that had the biggest change. So if nothing changes in our climate, things just keep going as they have been, eastern white pine will increase, aspen will decrease, black spruce will decrease. In a hotter scenario, so again, that 8-degree rise with very little change in rainfall, white pine does a little bit better, black spruce not quite so bad. And now red oak maple's kind of supplanting aspen as something that's making a little bit bigger change, at least as far as, right, the background algorithms are running. That warmer, wetter scenario, eastern white pine just likes it a little bit warmer, apparently, up here on the northern border of the state. Aspen now declines a little bit more. So it just jumped back in. Not that there wasn't a decline here, but it just jumped back in. The trend charts are where now you can kind of start seeing things a little bit more interesting. I'm just going to get in here and remove everything except aspen. So we can just take a look at that one species. So it's giving me all three of my climate scenarios, recent historic, hotter, warmer, wetter. So if nothing changes, climate just keeps going on as it was in the late 20th century, late 1800s. Aspen's going to decline from around 13% to about 8%. Under warmer, wetter declines down to 7.39, as that hotter declines down to 5.45. So hot, dry scenario, aspen is not going to do well. And so again, if you want to, you can click these on and off. And if I just want to see recent historic aspen and black spruce, how these things change. Or I want to put the hotter one back in, or warmer and wetter along with it. You can kind of see the black spruce declines very, very similar across. So it's just dropping down to that level. Again, distribution, the radar charts, maps. Again, you can kind of click things on and off. So we've got the hex bins, and you can kind of run these through time. So what does that look like, change through time? Or that scenario comparison. So 2030 for each one of these, recent historic, hotter, warmer, wetter. Again, you can animate them. The economic valuations are not building in, okay. And then again, same thing, the report. Now, in this case, I cannot generate a link because just the size of the data and how complex that landscape is. And I see Michael North is on. Michael, not just for you, but also want to take a look at wildlife and the Habitat Suitability Index. And so this was just now one of the Huckate watersheds that I selected. So again, kind of saw an area of interest, county, ecological subsection, and now just a Huckate watershed. So for forest management, we're getting all four of the forest management scenarios. The only climate scenario is that warmer and wetter, and I'm asking it for forest cover type. And again, forester, just that's something I can deal with. So what happens in terms of the forest? Okay, well, forest cover type. Oh, sorry. This is my wildlife one at accounting, sorry. So this is just how picking one climate scenario and how forest management will change the volumes. So again, You can kind of see if nothing happens to forest markets, forest products industry, we'll see an increase in the red maple oak, bur oak, see a significant increase, hard maple basswood, slight increase. If we increase harvesting, the red maple oak, about no change. The bur oak, we see actually a little bit more increase. And then the hard maple, basswood, same thing, a little bit more increase. If markets decline, again, not a lot happening. And it's really kind of the species. The max carbon sequestration, aspen shows up strong here, major decline there, major increase in bur oak. So it's just that change in management can make a big difference. So again, the trend chart and getting rid of everything, just because aspen's easy, but I'll keep aspen and I'll keep the oaks. You can kind of see a little bit better. So you can kind of see this decline in the aspens dropping down. Again, we see this red oak maple kind of actually peaking about 2060. Again, the mixed upland hardwoods kind of peak and then fall off a little bit, while down here the balsam poplar kind of across everything looks like a clear climate winner. Now, kind of running out of time here, so I just want to jump in quick of just demonstrating kind of wildlife. So looking at just a real simple, no change in forest management, climate gets warmer and wetter, kind of looked at game species, so mammals, game species, and species of greatest conservation need, birds of greatest conservation needs, and bird game species. So the HSIs generally are going to improve for mammals, not so much, and it's not a big change, but not so much for birds. Birds aren't necessarily going to do very well. And you kind of see, again, trend charts for each one of these. And again, these are habitat suitability indexes, not necessarily populations. Yep, I'll just run through the wrap up quick, and then we're going to head into questions anyway. So a couple things, been handling a lot of these scenarios and handling a lot of data, and there's some things that really stand out as we think about what does climate change mean, or how do these impacts of these forest cover type changes mean through time. And so this was really easy. This is the Minneapolis-St. Paul Weather Station, National Weather Service data from last year. We went into the winter in a drought status. Spring, we were in a drought status, but we got some rains. You can see there was some rainfall events here that were peaking up. But we had a 30+ day drought, extended drought, kind of that February into early April. We've got kind of extreme summer rains. There was a lot of precipitation, but it was all very large rainfall events, one almost 2.5 inches. And then this past fall, there was an almost 40-day event with no precipitation or extended drought. And you can kind of see it here of that August through early October, actually into mid-October. Now, statistically, we had near record precipitation, well above the normals or the norms. But all that rainfall, we had 2 extended droughts, and all the rainfall came across a concentrated period. There's a lot of danger when we say like hotter and wetter or warmer and wetter, saying there's going to be a 4-inch increase. What we're seeing is, and I'm sure you've heard this if you've been following kind of the climate modeling from the state climatologist office, we're seeing an increase in large flashy rainfalls. At the end of the day, an increase in rainfall does not necessarily mean increase in precipitation available to trees. Pretty much the trees experienced drought all year long last year, except for a couple of weeks here and there where there was adequate soil moisture. So I always like to say this, as we looked in the models, as we dug into why certain species weren't regenerating, the soils tend to be very dry in the spring. Spring-seeded species are not doing well, and it's a bit of asynchronicity, where seasons are a little bit earlier, they're a little bit warmer, soils are drying down a little bit quicker, and then we've been having these weird, again, it's just either we got it or we don't in terms of precipitation. Overall, the early successional spring-seeded species were really experiencing some real climate problems, at least in the models, that they were not regenerating from seed. Now, not everything regenerates from seed, but paper birch is something we try to regenerate from seed. Couple other things quick. Quaking aspen. We see this decline, and people say it's a climate loser, and I am not necessarily going to argue that. We're clearly seeing climate impacts on regeneration. But as you dig into the data, if you look at, so this is called the kernel distribution. This is just age classes, acres and age classes. So acres, age classes. There's two distinct age class groups, actually three, but we're not going to include that one, of kind of this clustered in and around between 0 and 50. But this very large piece clustered between about 70 and about 110. These stands are entering breakup and reinitiation, and they're converting to other species. It's not necessarily a climate effect. It's just an age distribution effect. And you can kind of see the impact of harvesting, right? We're keeping these acre levels, and my apologies, this is state lands only. We're seeing these harvest levels kind of modifying or moderating in and around this level. These stands probably aren't going to get harvested. If there's anybody on today that's harvesting 80-year-old aspen regularly, let me know. But these stands are probably going to convert over. And so there's both a climate impact as well as an age class impact. The last one is paper birch. And this is the one that worries me, that I keep sounding the warning bell on. Again, we've got this two distinct age class distributions. Again, we're seeing birch in that 100, 120, up to 150, 160 age classes. This stuff is going to convert. Anyone who's ever tried to regenerate 80-year-old birch knows it is very intensive. Doesn't mean you can't do it. It's just very intensive. These are the things that we might be able to hold on, but we're going to lose this. But as you can see, kind of going back to the harvesting history of where these things were regenerating and what's kind of regenerating now, we don't have a lot in the pipeline. And so when we see birch really not showing up well, it's a climate, it's forest products industry, and it's also this age class distribution that these stands are just entering breakup and reinitiation. So with that, I'll leave these for another day. Just say thank you to our team and thank you to LCCMR and ENTRF for funding this. Let's jump into the questions. I apologize, I didn't seem to leave that much time for it.
No worries, John. Thanks so much, and thanks for that additional context on the aspen and birch in particular. We do have a question from Laura. I love this project. Will you be making a simpler version of the simulation for people that are not technologically inclined, or maybe one that integrates with ArcGIS?
Yes. So the short answer is the 240-meter resolution upscale really created some problems. We are currently working through and would like to get to kind of downscaling this back to a 30-meter resolution, getting a little bit better description. And again, all things being said, there were over 6,000, almost 6,500 unique kind of 240-meter pixels within this. But we're going to be looking at probably maybe like St. Louis or Lake, guys, help us if you want, trying to downscale to 30-meter pixels and rerunning everything. So we are trying to see what we can't do. They're next steps. They're not funded, but these are just questions we want answered.
Thanks, John. And a question from Martha. Apologies if I missed this, but I heard that pest or pathogen data was not available in Landis when the modeling was done. If that data becomes available and is integrated into Landis in the future, will the ForCAST tool be updated as well?
We hope so. So there's a sub extension within Landis, and that sub extension wasn't available. It's being created. Brian Sturdivant with the U.S. Forest Service is the one creating that. It wasn't available to us. Hopefully, it will be in the near future, and we will. Because I will say this as you go in. I didn't say it before. I'll say it now. we are underestimating the amount of loss because those are not in there in tamarack and black spruce. We're still seeing loss insignificant, above 10% of acres, but I think it's much more than that. But we're underestimating it because we didn't have that extension available to us.
And just before I get to our next question here, just a quick heads up to call attention to the chat. I have pasted the link
Yeah.
for folks to fill out the CE request form. So follow that. I'll paste that again here just to bump it, but it should be available to y'all. A question from Christian: are the 100-plus-year-old birch acres largely theoretical? They exist in the models, but not in the woods.
Yeah, so this is something separate and I'll be happy to come back and talk sometime. So as part of this project and another project with the U.S. Forest Service, I've been working with the U.S. Forest Service trying to do an analysis of it's actually almost kind of criminal what we don't know about how long trees live. Most of what's in the literature is kind of awful. And I hate to say that, but it's kind of true. And so I've been working with David Wilson with MFRC and some others. There are within the lake states, both within Minnesota and within the lake states, there are birch stands. Not a lot. I think there's probably less than 20 that are over 150 years old. There is one stand, it's actually over in the UP, so it's Lake States data as well as Minnesota data. That's 220 years old. So they are out there. They're really uncommon. And so trying to figure out what kind of that natural range is, kind of not the outliers, the ones 5 and 6 standard deviations above the mean, but what are those that are 2 and 3 standard deviations above the mean? And so on an average stand, the last birch tree standing might get to somewhere between 120 and 150. But that's that key thing with Verlandis is what is that last tree standing that's producing seed? Because that's what we care about. Is it dropping seed, and is that seed going to contribute to that next stand of trees? But yeah, it's interesting data to work with.
Thanks. And I know you mentioned at the top of the presentation that this isn't really a stand level decision tool, but all the same, a question from Ryan here. What we've seen climatically on the landscape in recent decades, coupled with the data and modeling available via ForCAST, do you have any overarching management recommendations or principles for land managers to kind of guide them?
Yeah, I love paper birch. Please plant it. The thing that jumps out at me more than anything is statistically, at least looking at the numbers, there's going to be very little paper birch in the state by the year 2100. Drought adapted species are doing well. Mid-tolerant species are going to do well because they're growing into that state. The early successional species that we're so familiar with because of lack of markets, and I don't mean that in a bad way, they're still markets, but not what they used to be, back 50 years ago, 1970s. Of those stands that need intensive management to regenerate just aren't going to get it. And that's that key thing I say to everybody. We need to start thinking about investment. What do we value in the landscape? Are we going to invest? Again, for those of you who have tried to regenerate 80-year-old birch, you know what I'm talking about. Are we going to invest in maintaining some of these species on the landscape? The other piece is that range. What does that new range look like? And investing where they're going to be able to do well within that new range of certainly a warmer and what I would call at least droughty climate. So those are my recommendations. That bur oak's going to do well. Balsam poplar, find it, love it, grow it. Aspen will probably be okay because of our forest products industry. But yeah, paper birch is the one that I really worry about.
Thanks, John. And so that brings us to 10 a.m. We do have one more question, John, if you're available to stick around for just a
Well,
couple
yep,
more.
and I would say to everybody or anybody who's still online, Lane has got the full presentation. The links are all in there. It's recorded, and feel free to send me emails. I'm happy to talk and even walk people through. Hey, Nick, how you doing? Happy to meet with you just by a Zoom and kind of walk through an area of interest. So,
Great. So I'll just paste your email here, John,
yep.
in the chat. And then again, folks, please take a moment to fill out the CE request form if you haven't already. Thanks so much for joining us. Our next webinar is going to be on June 12th, so that Thursday at 9 a.m. But John, the question from Jamie Great presentation and great work. I'm wondering if there are ways to use ForCAST to get towards projected wildfire risks. High vapor pressure deficit has a strong connection to fire, and by using watershed soils, precip, or temp, you are getting close to VPD.
Yes. So I believe so, yes. Of Soils play a huge role. The Surgo, the NRCS Surgo database plays a huge role in this available water capacity, soil type. So kind of that combination of, right, what are those soils? How is the climate changing? And then what's that forest cover type? So again, right, and it's really more that piece, right? It's understory fuels. It's ground fuels, which we don't really have good data for, but ladder fuels and height to lowest dead branch. And there are some projects we're working on with some of our Forest Service partners. And actually, I have Pete Wolter, Iowa State University, where we're trying to get better information across a whole guild of species, the conifer species, to identify some of these things and build some fire modeling in, not necessarily to forecast, but into some other tools. And we'll be using Landis with that. So it's up on the Coishwee District in the Superior. Hopefully, lessons learned from that, we can break out a little bit farther across the entire state. So the short answer is it's possible. I'll let you know in 2 years.
Great, and that makes it my job easier. It's a lot easier to solicit webinars when the next one is plugged in the previous one. So, but yeah, thanks so much to everyone for sticking around here a little bit after the hour, and thanks so much to John for a really great presentation. I'll get this cleaned up and uploaded to the SFEC YouTube channel within the next couple of days. So look for that. Make sure you're subscribed to that so you get the ping. But thank you all again, and have a great week. Take care.